In this short video, I want to go over how would the graphs of the original function, its derivative, and its second derivative will look like. What did we learn about the sign line for the first derivative and second derivative, and how it can all be justified for some concrete example. And I chose a simple example, for example, a cubic function, x cubed. Here's the graph of the x cubed in front of you, and it's going to be my original function f of x. Now I want to plot y prime. Y prime or f prime will be what? Yeah, exactly, 3x squared. That's a derivative of the cubic function, and derivative of the cubic function now is a quadratic function, and it will be precisely its parabola concave up because 3 is positive. Here is the graph of the parabola concave up. 3 means that it's growing a little bit stretched up, basically the speed how fast it's going up. So the original function and its derivative. Now, before we start analyzing this, let's find a second derivative. What is the second derivative for the original function? If the first derivative was 3x squared, the second derivative will be, yes, 6x. That's a linear function. And the graph of this function is just a line. Now we can compare those three graphs and finally explain what did we learn and how all this can be applied if we know all the information. So I can see that the original function, a cubic function, is always increasing. If you imagine you're climbing the mountain, then you keep climbing, there's a point here where the slope of the tangent line is horizontal, and then you still keep increasing. So it means the original function is increasing from negative infinity to 0. At 0, it's neither increasing nor decreasing, and then from 0 to infinity. That is why, what would you expect from the first derivative? You would expect that the first derivative, f prime, be positive before 0, be positive after 0, and at 0, the first derivative will be 0, right? Because of the horizontal tangent line. Well, it's exactly what you can see on the parabola. What does it mean for the function to be positive? That means it should be above x-axis. So the first derivative, indeed, positive everywhere except 0. At 0, the first derivative is 0, just like we expected. So being an increasing function means its derivative will be positive or above x-axis. Now, what can we tell about the parabola? Parabola now actually is decreasing before 0 and then increasing after that. That means that the derivative of this function will be negative first, and since this is a derivative, then the derivative of this function will be second derivative of the original function will be negative, and then because this function is decreasing, and then positive because now it's increasing, and at 0 the second derivative is 0. Let's look what's happening with the second derivative. The second derivative is a line. I will even match the colors. Indeed, this part over here is below x-axis, so the second derivative here is negative. Indeed, it is negative. And then this piece is above x-axis, so the second derivative is positive. And then I will use pink color in the middle. Over here, the second derivative is 0. Not only this is important, let's talk about concavity. Let's look at the original function. The original function is concave down from minus infinity to 0. You see, how do I know that? Imagine if the rain pours down on this mountain, here it will fall down. The rain will be falling down from minus infinity to 0. So here the function is concave down. What does it mean for the function to be concave down? It means my second derivative, positive or negative? Yes, negative. You mentioned the grumpy face, right? So negative. And indeed, it's exactly what's happening below the pink part. I already showed that. The second derivative is negative from minus infinity to 0, which indicates that the original function is concave down there. Now, if I'm using purple color, it's not very different. If I'm using green color, from 0 to plus infinity on the original function, there the function looks like a cup, right? And if the rain pours down, the water will accumulate over here. It will start accumulating. So that's indicating that the function here is concave up. What does it mean for the function to be concave up? Its second derivative should be positive. You remember the smiley face, right? That's exactly what we already found out. The second derivative is positive from 0 to plus infinity. What this point over here at 0, 0 means, if it is in a domain, how do I know it's in a domain? Well, the function exists there. All inputs are allowed at 0 for the cubic function. There is no denominator that makes 0 to be 0 and so on. Well, if this point changed the concavity from concave down to concave up, that means the point changed the sign of the second derivative from minus to plus, then 0, 0. Then I can say that 0, 0 is point of inflection because it's changed the concavity. You can also indicate sign lines for both derivatives. For the first derivative, what kind of critical points will go there? You need to find where the first derivative is 0. Here's the graph of my first derivative. Being 0 for the first derivative means literally it touches x-axis. Those are what we call roots. So every time you have a graph like this, and it does its own stuff, all these points are called roots or solutions, and they have many synonyms. And that's exactly where your function is 0. So if this is my first derivative, then those are zeros for the first derivative. That's just an example. Then for the first derivative, the 0 point is my critical point. I will put it here, 0. That's my critical point because it's in the domain of the original function. No, actually, a critical point can be also a D and E point, but I mean that it is in the domain of the original function. And what are the signs of the first derivative before 0 and after 0? I take any test point, say minus 0.5. That's over here. At minus 0.5, you see the derivative is above x-axis, and it's some kind of positive number, maybe 0.7, close to 1, right? So that's my test point. So I'm choosing the negative 0.5 as my test point. And I can see that the derivative is positive. Then I'm choosing some kind of other test point. I can choose another one, like 1. That's over here. I'm going up and I see what's the output for that input. I don't need to know the number, but I need to know the sign. Well, it is positive because it's above x-axis, and actually something like 2.5. Positive. Then I can say that the original function is increasing, that's my f, increasing. At 0, it stops, and by stops means we have horizontal tangent line, and then it keeps increasing. So it's neither local maximum, not local minimum, even though this was a critical point. Remember that critical points are only candidates for the local extreme values. That's why we need to check them using first or second derivative test. Now let's do one more sign line for the second derivative, and you will see the idea is exactly the same. For the second derivative test, I still put 0 as my critical point. You remember that for the second derivative, we're using zeros from the first derivative. So this 0 is coming from f prime equals 0. Remember? These critical points are coming from the previous derivative. But now I'm taking test points and plugging them into my second derivative. That's why I call this second derivative sign line. For example, if I plug negative 0.5, it's over here. I'm going down below x-axis, and it means that the second derivative there is negative. I don't even need to know the number, but if you're curious, it's something like negative 3. I just know that it's negative over there. And then on the right hand side, maybe 0.5 is a test point. Here it is. Since I'm going up, it means that the output will be positive. If you wonder what it is, it's something like 3. But I just need the sign, positive. Then I can say, I will use the same color for the original function f. I can say that my original function is concave down, a grumpy one, from minus infinity to 0, and concave up, smiley one, from 0 to plus infinity. So all this information matches with the graphs we had before. It is indeed concave down, from minus infinity to 0, and then the green color was indicating concave up. Here it is. And this is how you compare all 3 functions. You can move on to the fourth derivative if you want, third derivative, fourth derivative, and all of these ideas will be taken into highest level anyways. The same situation happens between third derivative and fourth derivative. Fourth derivative is a first derivative for the third derivative. So everything will still make sense the same way. Fifth derivative is the second derivative for the third derivative. So it will show concavity of the third derivative, and so on. It's very helpful and interesting. Imagine that the original function was distance. The first derivative then will be speed or velocity, and the third derivative will indicate acceleration. And now we know that the speed was decreasing from minus infinity to 0, and then the speed started increasing from 0 to plus infinity. That means acceleration was always increasing, but sometimes negative and sometimes positive. Very interesting idea over here. Think about it more and ask more questions about this topic so that we can make more videos to illustrate those ideas even better. Thank you for watching.